Picture a void so profound it swallows light itself, a cosmic enigma that defies our understanding of reality. Imagine standing at the edge of a black hole, where time twists, space warps, and the universe's deepest secrets lie hidden. How many numbers would it take to describe such a monstrous entity? Millions? Billions? The answer might shock you, just three. Three numbers: mass, electric charge, and angular momentum, are all it takes to define a black hole, no matter its size, origin, or location in the vast cosmos. But how can something so complex, born from countless possible paths, be reduced to such simplicity? Where does all the information go? And what does this mean for the universe, and for us? This is the story of black holes, the most mysterious objects in existence, and the brilliant minds who dared to probe their secrets. From an 18th century English parson to a physicist defying the odds of a devastating illness, this tale spans centuries, blending science, wonder, and the relentless human drive to understand the unknown. So buckle up, hit that like button if you're as fascinated by the cosmos as I am, and let's dive into the abyss together. Don't forget to leave a comment with your thoughts. What do you think lies inside a black hole? And if you love exploring the universe's mysteries, consider subscribing for more mind-bending journeys. To grasp the strangeness of black holes, let's start with something familiar: the moon. Its surface, scarred by eons of asteroid impacts, tells a story of cosmic chaos. Each crater, from the vast South Pole Aitken Basin to the smallest pockmark, requires at least three numbers to describe it: longitude, latitude, and size. With thousands of craters, that's already thousands of numbers. Add the moon's chemical composition, varying across its dusty plains and rugged highlands, and the tally soars into the millions. A similar moon orbiting a distant exoplanet would bear a different pattern of scars, demanding its own unique set of numbers. Planets, stars, nebulae, each requires an astronomical amount of data to capture their essence. Now consider a black hole. These cosmic titans, capable of anchoring entire galaxies or devouring stars in a heartbeat, seem infinitely complex. They can form in countless ways: a star collapsing in a supernova, a slow accretion of dust over billions of years, or even the fantastical merger of every bit of knowledge from every civilization in the universe. Yet no matter their origin, whether in our Milky Way or a galaxy a billion light years away, they are defined by just three numbers: mass, charge, and spin. That's it. Three numbers encapsulate everything about a black hole, from the supermassive behemoths at galactic cores to the stellar remnants lurking in the shadows. How can such simplicity arise from such complexity? Where does all the information vanish? Let's embark on a journey through time and space to find out. Our story begins in the quiet English countryside of the 1780s, where John Michell, a country parson with a passion for science, pondered the heavens. In an era when Newton's laws of gravity were still reshaping the world, Michell dared to ask a radical question: what if gravity could trap even light? Newton had proposed that light consisted of tiny particles, what we now call photons. If gravity affected everything with mass, Michell reasoned, it must tug at these particles too. He knew light traveled fast, about 186,000 miles per second, as measured by astronomer James Bradley through the subtle wobble of starlight caused by Earth's orbit. But speed, however great, was not infinite. Michell imagined a body so dense that its escape velocity, the speed needed to break free of its gravitational pull, exceeded that of light. Such an object, he calculated, would be invisible, its light unable to escape, swallowed by its own gravity. He called it a dark star. Using Newton's equations, he determined that a body with the sun's mass, compressed to a radius of about 3 kilometers, would become such a star. For Earth, that radius would be less than a centimeter. Michell's idea was a spark of genius, far ahead of its time, but it languished as a curiosity tucked away in the scientific archives for over a century. Little did he know, he had laid the foundation for our modern understanding of black holes. Fast forward to 1915, amidst the horrors of World War I. In the trenches, German astronomer Karl Schwarzschild sought refuge in mathematics, tackling the freshly minted equations of Einstein's general relativity. Einstein's theory, a revolutionary leap beyond Newton, described gravity as the curvature of spacetime itself. Schwarzschild, desperate for an escape from the chaos around him, sought the simplest solution to these daunting equations: a single spherical mass in empty space. His calculations revealed a critical radius, now called the Schwarzschild radius, where spacetime warped so intensely that nothing, not even light, could escape. This was the event horizon, a boundary marking the point of no return. For the Sun, this radius is about 3 kilometers. For Earth, it's a mere 9 millimeters. Schwarzschild's solution was the first mathematical description of a black hole, though the term wouldn't be coined for decades. But Schwarzschild's discovery, like Michel's, was dismissed as a mathematical oddity. General relativity was new, its equations formidable, and the idea of an object so extreme seemed more fiction than fact. For half a century, black holes remained in the realm of theory, overshadowed by the rise of quantum mechanics and other scientific revolutions. It wasn't until the 1960s that a renaissance in black hole research would change everything, driven by new observations and a brilliant mind who would become a scientific legend. Enter Stephen Hawking, a name synonymous with black holes and human resilience. Born in 1942, Hawking was a bright but unremarkable student at Oxford until a life-altering diagnosis at 21, motor neuron disease, with a prognosis of just 18 months. Faced with mortality, he threw himself into his work with ferocious intensity, determined to leave a mark. Defying all odds, he would live until 2018, becoming one of the most celebrated scientists of our time. His contributions, particularly during the black hole renaissance of the late 1960s and early 1970s, transformed our understanding of these cosmic enigmas. Working alongside mathematician Roger Penrose, Hawking tackled the question of what happens when massive objects collapse under gravity. Could they scatter, or would they inevitably form a black hole? Their theorems proved that under general conditions, gravity's pull would overcome all resistance, collapsing matter into a singularity, a point of infinite density surrounded by an event horizon. This wasn't just intuition, it was mathematical certainty. Their work also introduced Penrose diagrams, elegant visualizations that simplified the complex geometry of spacetime, showing how light and causality behave near a black hole. These diagrams revealed the event horizon as a one-way barrier. Cross it, and you're on an inescapable path to the singularity, where the laws of physics as we know them break down. At the same time, advances in astronomy were bringing black holes out of the theoretical realm. Telescopes now lofted into space peered beyond Earth's atmosphere, capturing X-rays and other wavelengths. In the 1970s, a peculiar object called Cygnus X caught astronomers' attention. It was compact, incredibly bright in X-rays, and could only be explained by a black hole accelerating matter to near-light speeds as it fell inward. Since then, we've identified millions of black holes in our galaxy alone, from stellar mass remnants to the supermassive giant at the Milky Way's center, Sagittarius A star with a mass 4.3 million times that of the Sun, as confirmed by the Event Horizon Telescope in 2022. In 2015, the LIGO Observatory detected gravitational waves from colliding black holes, a discovery that earned a Nobel Prize and cemented their reality. But the true revolution came not from the skies, but from the blackboards, where Hawking and others began to unravel the thermodynamic secrets of black holes. If you're loving this cosmic journey, hit that like button to show your support, and let's keep exploring. What's the weirdest black hole fact you've heard so far? Drop it in the comments. Imagine trying to describe a human face. The curve of a smile, the shade of eyes, the texture of skin, each feature adds layers of complexity, requiring countless numbers to capture fully. Now, contrast that with a black hole. In 1915, Schwarzschild's solution described a non-spinning, uncharged black hole defined solely by its mass. By 1963, Roy Kerr extended this to spinning black holes, adding angular momentum. Add electric charge, and you have the full set: mass, charge, and spin. That's all. No texture, no color, no history, just 3 numbers. This simplicity is encapsulated in the black hole uniqueness theorem, a profound result summarized by physicist John Wheeler's quip: black holes have no hair. No matter how a black hole forms, whether from a star's collapse or the merger of galaxies, it's fully described by these 3 properties. This is astonishing when you consider the diversity of other cosmic objects. Stars evolve through complex life cycles, from blazing giants to dim white dwarfs, each stage marked by unique traits. Quasars, powered by black holes, churn out energy that would take trillions of numbers to describe. Even a small asteroid carries a unique history of craters and collisions. Yet Black holes, despite their varied origins, shed all distinguishing features behind their event horizon. But where does this information go? If a black hole swallows a library of every book ever written, does that knowledge vanish forever? This question, known as the information paradox, would drive physicists to the edge of known science. To understand this, let's draw an analogy to something familiar. A room full of air. You feel its temperature and pressure, but not the individual molecules zipping around. Those molecules, billions upon billions, can arrange themselves in countless ways while maintaining the same overall temperature and pressure. This number of possible arrangements is called entropy, a measure of a system's internal complexity. For a gas, entropy grows with volume. More space means more ways for molecules to move. Black holes, surprisingly, also have entropy, but it's tied not to their volume, but to the area of their event horizon. This discovery, pioneered by Jakob Bekenstein and Stephen Hawking in the 1970s, revealed that black holes are thermodynamic objects with properties akin to temperature and heat. This was a game changer. If black holes have entropy, they must have a temperature. But how can something that swallows everything, even light, emit heat? The answer lies in one of the most mind-blowing discoveries in physics: Hawking radiation. Let's dive deeper, and if this is blowing your mind, smash that like button and share your thoughts in the comments. What's the craziest thing about black holes to you? Picture a black hole, cold and dark, a void that consumes all. Now imagine it glowing, ever so faintly, with a temperature hotter than the core of a star. This is the paradox of Hawking radiation, a discovery that turned black hole physics on its head. In the early 1970s, Bekenstein, a student of John Wheeler, grappled with a problem. The second law of thermodynamics states that the universe's entropy must always increase. Mixing hot and cold tea increases entropy, but if that tea falls into a black hole, does its entropy vanish? Bekenstein argued that black holes must have entropy, proportional to the area of their event horizon, to preserve this law. Hawking took this further, proposing that black holes have a real, measurable temperature. But how? Black holes were thought to emit nothing. The answer lies in quantum mechanics, specifically Heisenberg's uncertainty principle, which reveals that even empty space isn't truly empty. Near a black hole's event horizon, the vacuum can borrow energy to create particle-antiparticle pairs, like two photons. Normally, these pairs annihilate each other, returning the energy. But at the horizon, one particle might fall in while the other escapes. The escaping particle carries energy away, reducing the black hole's mass, while the infalling particle ensures energy conservation. This process, calculated by Hawking, produces radiation with a thermal spectrum exactly like a hot object. Black holes, it turns out, are not black, they radiate. The temperature of a black hole is inversely proportional to its mass. A stellar mass black hole, like those in Cygnus X1, has a temperature of about 10 to the minus 8 Kelvin, near absolute zero. But a hypothetical black hole the size of Mount Everest would blaze at billions of degrees. As black holes radiate, they lose mass, growing hotter until they evaporate in a final burst of energy. This raises a new question. What happens to the information swallowed by a black hole? If it evaporates completely, is that information lost forever? This is the heart of the information paradox, and it's where our story takes a surreal turn. If you're as hooked as I am, hit that subscribe button for more cosmic mysteries, and let me know in the comments. Do you think information survives a black hole? Imagine dropping a book into a black hole. Its pages, filled with knowledge, spiral toward the singularity, where space-time itself seems to collapse. Is that information destroyed, or does it persist in some hidden form? For decades, physicists debated this question. In quantum mechanics, information is never lost. Yet Hawking's radiation appeared featureless, carrying no trace of what fell in. The answer emerged from an unexpected place: the holographic principle, a radical idea that suggests the universe might be a projection, like a hologram on a cosmic screen. The clue lies in black hole entropy. Unlike a gas, where entropy scales with volume, a black hole's entropy depends on the area of its event horizon. This is bizarre. For a gas, more volume means more ways to arrange molecules. For a black hole, it's as if all its complexity is encoded on its two-dimensional surface, not its three-dimensional interior. In 1995, physicists Andrew Strominger and Kumran Vafa explored this in a five-dimensional mathematical universe using string theory. They counted the microstates, possible internal configurations configurations of a stylized black hole and found they matched Hawking's entropy formula exactly. This suggested that a black hole's information isn't lost, it's stored on its horizon. The holographic principle, formalized through the ADS/CFT correspondence, takes this further. It posits that a gravitational system in 3 dimensions can be fully described by a non-gravitational system on its 2-dimensional boundary. Imagine the universe as a sphere, with all its physics encoded on its surface, like a hologram projecting a 3D image. For black holes, this means the information of everything that falls in is preserved on the horizon, encoded in the subtle correlations of Hawking radiation. While we can't yet apply this to real-world black holes like TON 618 with its mass 66 billion times that of the Sun, as observed in 2025 data, the principle offers hope that information survives. So what is a black hole made of? For a gas, we can point to molecules. For a black hole, the answer is elusive. Crossing the event horizon to probe its interior is a one-way trip. No signal can escape to tell us what's inside, yet mathematics offers a glimpse. Strominger and Vafa's work showed that in a simplified universe, black holes could be built from string theory's brains, their configurations accounting for the entropy. But for real black holes, we're still in the dark. Are they made of quantum strings, pure geometry, or something else entirely? The question is not just academic, it challenges our understanding of reality itself. If we could peer inside, would we find a chaotic soup of quantum states or a perfectly ordered structure? The answer lies locked behind the horizon, a secret the universe guards jealously. Consider the journey of a single particle falling into a black hole. As it crosses the event horizon, it's stretched and torn by tidal forces, its information seemingly lost to the singularity, yet the holographic principle suggests this information is smeared across the horizon, encoded in a 2-dimensional pattern like a cosmic QR code. This idea is mind-bending, a 3-dimensional object with all its complexity reduced to a surface projection. It's as if the black hole is a cosmic vault storing every bit of information that enters, not in its depths, but on its boundary. Recent advances, like the 2023 breakthrough in quantum gravity simulations, hint that these correlations in Hawking radiation might one day allow us to decode this information, reconstructing the particle's history from the radiation's subtle patterns. But for now, the interior remains a mystery, a puzzle that drives physicists to push the boundaries of theory and imagination. As of September 3rd, 2025, black holes remain the universe's greatest enigma. From Michel's dark stars to Hawking's radiation, each discovery has peeled back a layer, only to reveal deeper questions. The Event Horizon Telescope continues to image black holes, capturing stunning visuals of Sagittarius A star and M87, while LIGO and its successors detect their collisions, with over 90 confirmed events by 2025. Yet the interior remains beyond reach. The holographic principle hints at a universe where information is never lost, but the full picture awaits a theory of quantum gravity. Perhaps future observatories, like the planned LISA mission launching in 2035, will detect gravitational waves from primordial black holes, offering new clues. Until then, black holes taunt us with their simplicity and complexity, a paradox wrapped in an enigma. The story of black holes is also a story of human curiosity, from Michel's quiet musings to Hawking's defiant brilliance. Each step forward has been a triumph of intellect over the unknown, a testament to our drive to understand the cosmos. Black holes are not just objects, they're gateways to rethinking reality. They force us to confront questions about the nature of information, the structure of space-time, and the limits of physics. The holographic principle, born from black hole entropy, suggests our universe might be a projection, a 3D illusion encoded on a 2D surface. This idea, explored in 2024 experiments with quantum computers simulating ADS/CFT systems, could redefine how we view everything from particles to galaxies. But the journey is far from over. As we stand on the cusp of new discoveries, black holes continue to challenge us. Upcoming missions like the Square Kilometer Array, set to revolutionize radio astronomy by 2027, promise to reveal more about the environments around black holes, from accretion disks to relativistic jets. Theoretical advances like those in loop quantum gravity aim to describe the singularity itself, potentially unveiling what lies at the heart of these cosmic beasts. Every answer raises new questions. If information is preserved, how do we access it? If the universe is holographic, what does that mean for our place in it? Black holes are a reminder that the universe is vast, strange, and full of secrets waiting to be uncovered. This journey through the cosmos shows us that black holes are more than voids. They're gateways to understanding reality itself. They challenge our notions of space, time, and information, pushing science to its limits. So, what do you think? Is the universe a hologram? Can we ever know what's inside a black hole? Drop your thoughts in the comments, hit that like button if this blew your mind, and subscribe for more cosmic adventures. The universe is vast, and we're just getting started. Let's keep exploring together. Share this video with a friend who loves a good mystery, and tell us in the comments, what's the next cosmic puzzle you want us to tackle?